Okay, so actually today we're going to be talking about the last bit of our stats, which is correlation and regression. But I'm actually going to first make a couple of announcements. So last class I mentioned, but I forgot to post. So since more people are here today, I will remind people that I'm actually going to have a small take-home exam online as part of finals week, because I want to make sure that you actually go back and really study some of the stats and the experimental design. So the only thing that will be on the exam are the lectures I gave on the material in this class. So what is experimental design, a little bit about how to do research, who knows, maybe even a LaTeX question, all the things I talked about. There will be probably what I expect will take you half an hour, but I will give you unbounded, no, I'm not going to give you unbounded amounts of time. Because if I gave you unbounded amounts of time, you wouldn't have to study. You could simply go look it up in real time. So I will have to think about exactly how much time I will give you. I'll make it a timed Blackboard exam, but you don't have to come in during finals week. It'll just be, also your paper is due on basically class time during finals week. Right? So you'll have two things due that week. The paper will be due, and then during our finals period, which is I think 5:20 to 7 or something like that, we'll have our online final exam, but you do not have to come to class to do it. It's not terribly long, and the grade is one of three: A, C, or F. Okay? So I'm not going to, it's not going to be a very fine grade because there's only going to be like 10 questions. So it's really hard to give very fine grading when you have a very sparse sample, right? So it'll either be, yeah, you got these mostly right, you got them around half, or you got less than half. Those will be the three sort of choices of what's going to happen. So your final paper, so a bunch of you did turn stuff in on Friday. I apologize, I have not gotten back to most of you who did, and if you didn't turn it on Friday, I haven't even downloaded it yet. I had a bunch of other stuff that sucked up part of my weekend, and we have 3 more faculty candidates to go and 3 down, so I actually didn't realize how much time I would be spending with all of that as well. So, but you will get feedback sometime this week for those who turn it in by Sunday. So I've started reading them, but I want to read more before I give individuals feedback, so I'm a little more consistent in what I'm doing. Your presentation is 20 minutes with however long we take for questions, so it might be half an hour of questions. So be ready with understanding what you presented. You are presenting your paper, right? Not somebody else's paper, but if your paper is a survey, you will be talking about other people's papers. If you're presenting your own work, you're still probably talking about some other people's work because you have a related work section of your presentation. Okay? You should reasonably understand the related work of your work, so they all become fair game, right? In terms of me asking questions, right? I might have looked at the papers you're citing because I get to see your draft papers. So, so you should be pretty familiar with what's going on with those. You'll be being graded because I didn't give you a rubric. No one asked, or if they did, I didn't answer. But you can be graded a little bit on presentation. And I will give you some feedback today after Bob is done because I expect he'll do an excellent job, so we don't have but mostly you're going to be grading on, did you have the right content in your presentation? Okay, I'd say that's 70% of your grade, 30% is your ability to actually present it, because we haven't spent time on doing presentations in this class. If there's time at the end of class, because I think there will be, I will talk a little bit more about that. So before I get into new statistics stuff, especially given that there will be sort of a quiz at the end of the semester, did anyone have questions from last week? I covered a lot of statistics in a very short period of time. No questions. It was clear or non-understandable, one of the two, not somewhere in the middle. And I'm going to go with it was non-understandable. So I'm going to ask you some questions since no one had any of me. So what's the goal when we're trying to do experimental design and its relation to statistics? What is one of our goals when we're designing our experiments vis-a-vis statistics? There are 2 things that I said last week.
It needs to be statistically significant.
Our goal is to design an experiment for which we can measure statistical significance. The goal is really, you can say the goal is to be significant, but at a minimum, we want to design one so that we can measure statistical significance. Because if the answer is the hypothesis doesn't hold, it might not be statistically significant. But if I didn't design it to be, it is unlikely to be, that I can measure proper statistical significance if I didn't design an experiment to do that. So that's the first goal. And ideally, Bob is right, we want our results to be significant because we want to have designed it to answer our hypothesis. But sometimes the world doesn't play along. You think your algorithm is better, you run it, you find out it's not, or you find out you can't say that it is. Those are the breaks, so you get a different problem. But if you design it properly, you can make it more likely that it will. Okay? There's a second thing about experimental design, which is actually the more subtle one, which was actually on the slides, because it was a little less obvious, which is one of our goals is to design our experiments to reduce variance. Okay? Why do I want to reduce variance if I want to do statistical testing? Anyone? Well, actually, I can have something that's extremely repeatable and have high variance, right? But why might I want to try and reduce variance? So what statistical tests do we talk about? T-test? And remember, what's the T-statistics formula? That's going too far. I won't ask you for a formula on at the end of the semester, because you can always look up a formula. That's not my goal. But the basic T-statistic is like x1 mean minus x2 mean divided by some standard deviation. Standard deviation 1 or standard deviation 1 plus standard deviation 2. Right? The reason for T-tests, we really want to reduce variance, is this is on the bottom. If this gets bigger, our things become less significant because this number becomes closer to 0. Right? If I have two means, I had this drawing, right? If I have two means and they're pretty close together, right, and they have high variance, it's hard to say whether or not these differences are significant. If I have the same means with these two distributions, they're significant, right? So this is about making sure when you're doing your computer science stuff, you try and control sources of variation that are not inherent to your problem. Okay? This is one of the places where we as computer scientists often have tremendous advantages in using statistics compared to other fields. Right? Now, those of you who are going to deal with humans, you don't get that advantage because humans are your biggest source of variability. But even with humans, you can design experiments to reduce variability by doing things like control groups that are matched on skills. If I just run 50 people through a user interface, and I don't separate out novices from experts, I will have a huge variation. But if I put them in bins and I refine my hypotheses, then I can have only experts using it, only novices using it, and the novices will have more variation, but not near as much as if I have novices and experts, because there's a very natural variation. So you can still design even your human experiments to reduce that. So there's a bunch of stuff in the experimental aspects that go with it. Okay? Now, the next thing we're going to talk about is another place where computer scientists have tremendous advantages compared to the rest of the world, the physical, natural sciences, because when we talk about correlation and regression, we get to control a lot more about what our models do. So the first part of this, I'm going to do very classic, here's what stats talks about, and then I'll come back to a little bit more about what's different in how we do this in computer science. Okay, so I'm going to talk about here what are called non-spatial approaches to correlation and regression. And I just want to point that out because some of you have also dabbled a little bit towards computer vision. In computer vision, we talk about another thing, which is spatial correlations, okay, and signal correlations, which are related but different. And so I want to just sort of separate that out. We're not talking about signal processing correlations, or what are oddly enough called spatial because they're really looking at waveforms and whatever. We're looking at mathematical correlations. So we're going to look at correlation and regression. And so first, what's the difference? Mathematically, there isn't one. There are actually two different terms for two mathematically identical concepts, but very different ways of looking at them, interpreting them, and sometimes computing them. So correlation stands, as its name, the core in correlation is because of the covariation. If I have two variables, there's a relationship between them. If I have two variables, x and y, as I have in this plot here, there's a correlation because as this axis grows, the data tends to move downward, right? So as I increase x, I decrease y. That means they are negatively correlated. Okay? And in correlation, the normal way when people use the word correctly, there is no direction. There is no causality. Okay? Lots of people, however, confuse correlation with causality, especially if I have correlation in time. If yesterday's event and today's event are correlated, people will think they're causal. What happened yesterday caused what happened today. And we talked a little bit about this before. That doesn't have to be the case. What happened today and what happened yesterday could both be dependent on some third variable we've never talked about, and they actually have almost no direct relationship, but they can be extremely correlated. Okay? But the causality is this causes this causes that. Okay? In fact, if I think of something that is completely causal, like there's a curve in the world, and I sample it one day, and I sample it another day, they will become correlated based on whatever the underlying signal is, but one didn't cause the other. They're both just samples. And to me, that's the easiest way to keep clear what's going on with correlation. Correlation is looking at samples and saying, this sample and that sample have a correlation. I've sampled something in the world, and there is something that makes them related to each other, but not necessarily that one is causing another. Regression is actually a term where we say, I'm going to, given the value of x, I'm going to predict y. So I'm going to predict y from x. Okay? Mathematically, it's the same relationship. I'm using the correlation. In this case, I'm going to look at the x value, and I'm going to use that to predict what's the y value I would see. I can actually do the same. This is the same data. I could do that up here. Correlation and regression have the same relationship, but people who are doing regression normally imply, often incorrectly, causality. But even if you're going to use it in a computer science point of view, you don't have to worry about causality if what you really mean is predictability. What it really suggests is, given x, I can predict y. That has value in computer science, independent of causality. The people doing physical sciences and natural sciences, prediction isn't enough for them. They want to understand what's the cause of this, what's the why. Computer scientists like whys, but very often we can get by with, it doesn't really matter. If I can predict what's going to happen, that's the most valuable thing to me. So in that sense, regression is the tool we as computer scientists use most often. But I also wanted to make it clear, it's really the same as correlation. Correlation is just a linear way of relating, or linear correlation, which is most of what we'll talk about, relates to two variables.
Are you going to get into variance and regression in the...
Yes.
Right, okay.
So we'll talk a little bit about that, and how to interpret statistical significance of regression is part of what we're heading towards. Now, when you're writing papers and when you're reading papers, many people will imply, right, that if I can predict y from x, it implies it doesn't prove causation. Okay? Lots of papers will say, I have now shown that x causes y because they've done regression. It is a classic beginner's mistake, or it is somebody who's trying to claim more broadly even though they know better. Hard to tell when you're reviewing papers or when you're looking at them. But regression never proves causality. Okay? I wouldn't even say regression implies causality. Okay? The only way to imply causality is to have designed an experiment where this variable is truly an independent variable. If I can control it, if this is a knob that I can control and show that when I move this knob independently, this responds, then I'm implying causality. I'm still actually showing causality, because if these two are connected by a wire, and I move this one, and this one moves, and that makes that one change, right? So causality is still not proven, even if I have a truly independent variable, okay? But if I call x my independent variable, and I controllably change it, then I'm closer to actually implying or measuring that there's a causal effect. Right? If I do this, it causes that. That's what we mean by causality. So if I push this knob, I cause this, door to open, right? That's close enough to causality for most people, even if the real answer is when I push this knob, a monkey sees me do it and opens the door, right? I didn't actually cause the door to open. I don't know what the mechanism connections are. You need more complicated experiments, but it's enough to get there. The problem is people will then use the phrase, well, X is my independent variable, but you know what? I can't actually control this. I'm going to observe X, and then I'm going to observe Y. And that suggests that there's causality. Okay? Just because I observe one first or call it my independent variable doesn't make it causal. And this is probably one of the biggest mistakes people make playing with regression. And the worst part is that many of them do it because they've read papers and they're mimicking that. Okay? Good papers won't do that, but there'll be lots of mediocres and lots of bad papers that will. So I want to make sure you get that part clear. So when we talk about correlation, the variable that is probably the most common statistic in all of science is what's called the correlation coefficient, generally measured or called the variable R. I have no idea why. And it measures the strength of the relationship or the association between two variables. For example, income and education. So if I have an increase in this variable and I get an increase in if I increase the independent variable and I get an increase in the dependent variable, then we say they are positively correlated, and I'll be over here. Increase goes with increase. If when I increase one, I decrease the other, then they are inversely correlated or negatively correlated. Okay, so a +1 implies perfect positive association. If I change one, the other moves exactly the same way. Okay, still doesn't prove causality because if they're tied directly to this variable, which is the one that's causing both of them to exist. Okay, now that doesn't mean the variables are the same. Imagine that I take one signal, and I add a constant to it. Okay, then the values are completely different, right? But they're perfectly correlated because every time one's changing, the other's changing. So for every value I measure, there will be a strict correlation. So for example, for income and education, improving income and improving education are positively correlated. Okay, people with higher incomes have higher educations. That doesn't prove that more money leads to better education. It might be that better education produces more money, right? Or that the parents who have money had a higher education, which is now this indirect variable, right? Parents who have a higher education push their students towards better education and produce better incomes because they have there's a whole bunch of things that can go wrong. So you have to be very careful, and that's why I like to use this example instead of because everyone can relate to it. So if I have a 0 in my correlation, it means there's no association, right? So a classic thing if you're doing stock portfolio balancing is to minimize the correlation among different things. We'll come back to why that's valuable. For lots of different experiments, decorrelated variables improves diversity, which means under bad circumstances, only one of them fails and the other. And you can use some of that in experimental design. And then if one goes up, the other goes down, that's negative. Whoops. Okay, now the name correlation coefficient, if you actually go looking for it, you might find 5 or 6 different correlation coefficients. So the formal name for this one is actually the Pearson product moment correlation coefficient. Mostly it is called the correlation coefficient, but if you fire up a stat library like R, or a software package like R, and you look for correlation, you might find a whole bunch of different ones. So I just want to make sure if you need to choose it, you're looking for the one that's Pearson product moment correlation coefficient. So just to make sure you have an understanding of what they mean. So this is near perfect correlation, right? Or it is perfect correlation, R equals 1. If I have a cloud that looks like this, it's a very strong positive correlation. So R is 0.72, and it means for every change in one unit, you have a 72% chance of predicting, really, the other variable, right? So you're not going to predict it perfectly. Your error will have some range, but it's pretty good. Here I have something with a weak correlation. I don't know if you can see, there's actually a blue line in there, right? That's the actual best fit line, and it has a slope. This is 0.26. Okay, this is weakly positive. And in computer science, weakly positive is common, but not huge. 0.26 in various places in psychology is a huge correlation because there's so much other stuff going on. So it also depends a little bit at the field. What related experiments find for correlations would be important. Here we have a strong negative correlation, then we can have perfect, right? So it's really the slope of the line. If I fit a line, the slope of the line is the correlation coefficient. If I do the best fitting line, under the right rules for best fitting line, the slope of the line, 1, 0, minus 1, right? It is R, okay? So if you're thinking mathematically, it's easier from, I always think of it as the slope of the line, because it's more the way I think about things. So if I looked at things like correlation coefficients, this is from China, data from China, rural per capita income related to urban income, and you look at the two different incomes, you'll find that there's a very strong, in the different provinces, right, there's a strong correlation. So the question for these people isn't urban versus rural, but which county do you live in? Rural counties, urban counties, there's a relationship between them, right? So there's all kinds of correlations that exist. I don't think there's any reason to believe they're causal, right? They're just relationships. So the formula for calculating it, by hand, I don't expect you to ever do it. You would just use a tool that can compute it. But the reason to talk about it is for the same reason we talked about it for the t-test, right? So here's our correlation coefficient. It's the sum of the products of xi and yi divided by n. So this is really the average of the products, hence the name Pearson product moment. Right? It's going to take the product of each of the two variables, sum all up all the products, and then divide by n, so the average product, minus the product of the averages, divided by the standard deviation of each of the two data sets. Standard deviation of x, standard deviation of y. Okay, so before the days that people had computers, this is how people did it. You did it by hand, you actually compute all this stuff. Today, I wouldn't bother with these formulas. But the important part about these formulas is the fact that just like our t-statistic, you'll notice we're dividing by the standard deviation. So again, if I don't control random variations in my data, I reduce the power of this statistic to do anything else. Because if I take the same best fitting line, and I'm close to it, and the same best fitting line, and I'm far from it, where now I have a large standard deviation, this one, even though they have a slope of the line, right, and this one. So it turns out that as I go to do this, as my data gets farther and farther apart, even though this is what I would like to think of as the best fitting line, okay, this is not how we do the best fitting line for this problem. So if you remember your class, or maybe you don't, but when you go to do a best fitting line, there are two ways to measure error. Okay, can anyone think, what are the two ways of measuring error of the distance of a point to a line? Well, standard deviation is a formula that says what's a bunch of stuff. But if I'm going to measure the error, if this is my prediction line, and here's my point, what is my way of measuring errors? Well, least squares, they're actually both are least squares. So there's two answers, or three, but the most common two are to go up to here, right, and just consider the direction in the variable y, which is what we would call a prediction error. If this is my value of x, and I predicted y, then this is my prediction error, okay? But if I'm going to do least squares fitting of a line, I can either do it like this, or I can do it like that and choose the point on the line that is closest. So there are two different line fittings. When I say R comes from the slope of the line, it comes from the formula for the line if I fit it the right way, and it's not the same as if I fit it the other way. If I take 2 points, two sets of data, if I were to take this set of data and I add 1 point over here, so this is my new point, the best fit line now looks like this. 1 point pulls everything off because of this square error. If I'd gone way out here, this error is huge. Right? So it's going to actually choose it so that this error equals the sum of all those. So that's probably a little too aggressive. There's a lot of points there. But it'd be something like this. So it's going to change where the lines are. So variance, which is also a large effect of how far away the points become from the line, has a big impact on what your slope is going to end up being when you do the regression. Okay, so simple regression, which is actually easy. is really two variables, x and y. That's the way we've been describing stuff. Multiple regression, which is actually quite common for computer science, is between three or more variables. We're going to have one dependent variable and two or more independent variables. Okay, and now it becomes important that we distinguish between independent and dependent. So if we think about gender, education, and income, right? Now, this is actually an example of why these aren't truly independent variables. Can I change this one? Not really. Can I change that one? Yes, that one I can actually change. But most experiments don't do this. They sample these, and then they talk about income. Right? But these two in this drawing are the independent variables. Nicely in computer science, I can actually do stuff where this axis might be something like the data size. Like how many points do I include? This might be cache size, and then this could be performance. Right? Now these are truly independent variables. I can change the size of my data, I can change the size of my cache, and I can measure my performance. So we can often get truly independent variables. It's tricky. So now if I'm going to do independent variables for multiple regression, right, what do I get? Do I get a line? So think about it. If I were to measure for each value of the size of data and for each cache, right, what I would get above this wouldn't be a line. It's a plane, right? Because I've sampled for each of these points, right? I get a whole bunch of data. I get a plane. Okay. So when we go to actually do that, it's still a linear fitting problem because what I do is I take my two-dimensional data and I find the best fitting plane. And obviously, if I have three-dimensional data in terms of three independent variables, and I fit one dependent variable, I get a hyperplane, right? And so the dimensionality, it's all linear fitting for multiple regression. Now, I want to contrast that with another thing we sometimes do, which is I change one thing and I get two measurements. Right? Because I can change the size of my data and I might get both time and power, or time and latency. Okay? So there's still three variables, right? I have data size, time, and latency, or maybe even data size, cache utilization, and performance, right? Almost the same three variables. One was cache, whatever, but now it's cache utilization. Those are two dependent variables, cache utilization and time. I change my data size, okay? So what am I doing if I have that? If I have one variable, one independent variable, and two dependent variables, what am I fitting?
I would need two simple regression.
Right. Yeah, so you actually have two regression problems. So if I have x1 goes to y1 and x2 goes to y2, right? I can just treat two of those as two separate regression problems. But that does still miss something. What did I miss? Well, I might have missed that there's actually a relationship between these two. Okay? So I could actually still do another regression. So I can do three simple regressions. But this is a little bit like a problem we had when we were talking about doing t-tests, right? We moved to ANOVA because multiple t-tests have a chance of finding interactions that don't really exist by random chance. So in higher dimensions, I can still go from, this is actually one variable, right? I can go from one variable, and I can fit each of these two. Okay? Or I can take these two variables and fit that one. Because we're looking at a linear relationship, right? It doesn't, again, we talk about correlation. Correlation, you give up the idea that one tells you the other. But if I'm really trying to understand the relationship between these two variables, I can fit these two predicting x1. And if you think about the way linear prediction works, if I can predict one way, if this is my line, I do prediction by looking up this variable. You tell me x, I'll tell you y. Well, guess what? You tell me y, I can tell you x. Okay? As long as the line isn't degenerate, right, you can do this. So if there's a relationship between the variables, which means this line has a slope, then I can predict one from the other. And this gets back to, right, it's not really causal. even if I chose the pool size, I can talk about the relationship between these two going the other way. So we always think of multiple regression as multiple variables versus one outcome. So it's always fitting a plane, a hyperplane, or whatever. How you want to interpret whether or not it's causal and what it means, and what's truly independent and dependent variables, that's a different thing, right? But if you're trying to find the relationship, it's there. Okay. Now, if I have a plane that fits a line, so if I have two variables and I'm fitting this plane, and all I care about is predicting it for one value, that's really just slicing the plane in one point. Still very doable. So even if I fit it the other way around, I can get a line fit for any particular value of x1 that I want. But I can also fit it for lots of other values, so it has more power to go that way. Okay, so talk a little bit about what the errors are and what some of these mean. So simple linear regression, which is really predicting one variable, y, from the other variable, x. And our function is a form of, is written down as y equals a plus bx plus e, or epsilon. Okay. Now this is a form of the line. Oops, all right, just erased what I think it's on the next slide. This is really y equals mx plus b, right? When you learned about lines, that was the first form of a line, right? Y equals m, which is in this case b, so just difference of labels, bx plus a plus epsilon. Epsilon is our error. So a is the intercept, b is the regression coefficient, the slope of the line. And it changes for y with 1 unit change in x. And epsilon is our residual error. Okay? And the residual error is the difference summed over all the data between the actual value of yi and the predicted value of yi. Right? So if this is my line, if this is our regressor, if here's a point on the line and here's the actual point, here's our prediction, then that vertical distance sampled this way, right, just per vertically, is the error. Okay? And this is what we call ordinary least squares. And that's the standard criterion for obtaining a line doing this type of regression. Okay? We're going to try and find the value such that I minimize the sum of the squares of yi. Okay? And this is the standard regression line then. Now, the one that uses the normal representation of a line, where they measure direction, so what's called normal least squares, which is oddly enough not the most common one. They mean normal in the direction of the normal of the line sense, not normal as the one people normally use. We use ordinary for that one. So you get a different formulation and a different line. Right? So statistics, when we talk about regression, we normally do ordinary least squares. If you're using data and you really have no control over the two variables, so if I choose this axis, I chose x, right? X is my data size, right? Then I know this exactly, and I don't expect there to be any noise in this direction, in which case measuring error from predicted to here in this direction makes sense. That is the only place I can have error because this is something I chose and I measured it exactly. However, if I'm observing in my experiment values, if this is measured and this is measured, then I could have had error in this measurement. And if I could have error in this measurement, then maybe what I really want is if this is the line, use this point, because this minimizes the total error between x and y. Okay, that's why we sometimes use total or normal least squares. And so in computer science, however, most of our experiments, we get to choose our independent variable, so we want ordinary least squares does make sense.
What was the second one called? Ordinary?
So this is called ordinary. This is called either normal or total least squares.
Normal makes sense.
It's the normal of the line, yes. And they call it total least squares because it's actually the error in this direction and the error in that direction.
Oh, okay.
So the coefficient of determination, which we call r squared, measures the proportion of the variance in y, the dependent variable, that can be predicted or explained by x, the independent variable. Okay? So this r is not the same as the slope. Okay? And this is one of the places where I get very confused as a dyslexic, because the correlation coefficient here, earlier when I said R is the slope, in some formulations, R is the slope of the line. In other places, R is this, right? R squared is what they call the coefficient of determination. The two are related, but one depends on the variance, right? So this one is the variance explained by one compared to the other. The formula for that is the sum of y hat minus, so the raw data, minus the mean squared, which is really just the sum of the squared errors for the regression, divided by the total, or the sum of the squares, which is yi minus y hat. So here, or by y bar, right? So this is both y bars, both have the average of y, but this one uses the raw data and this uses the predicted data. So this is the sum of my predicted squared errors divided by the variance of the raw data. And if you expand this out, you'll see that there's the total sum of squares, which is equal to the regression sum of squares plus the residual errors. So these two, right, are just an expansion of the total sum, which relates them. So when people talk about it, right, the coefficient, the more the deterministic the line, okay? And so, as I said, right, the slope tells me one thing. It tells me the relationship about the variables. How much a change in this variable affects a change in that variable. But the coefficient of determination, the R squared, says something about how tight is this. Even if I have the same line, same slope, this one will have a much larger R squared because it has larger variance. No. Oh no, smaller. Right? Because the top one, the tighter one here, has smaller total sum of squares. So this bottom number becomes smaller, and the top number becomes larger, or stays about the same. So when we think about partitioning the variance, so which is what we call least squares doing, or sorry, the coefficient of determination R squared is measuring, right? We have the total sum of squared errors, right? So I have the distance for each of these. The distance of the point y squared from the bottom, right, can be broken up into two pieces. The distance of the line from the axis plus the distance from the line to the actual data point. Right? And that's what the partitioning is sort of saying, that if I take the raw total sum of squared errors, I get it as a combination of the distance from the line plus the distance of the line from the data. So that puts the two together. And then R squared is really just this ratio, right, of the regression or the explained error versus the total error. So it's this error divided by the total error. Gives us those two. Okay, so the standard error estimate, okay, which we say measures the predictive accuracy, the standard error is greater than the spread of observations on the line, thus the predictions are less accurate. So the standard estimate of the standard error is the mean square error or the average square residual, which is also equal to the variance of the estimate and the variance about the regression line. So our standard error is the regression error, yi minus the predicted value squared, sum of the squared error, sum of the squared residuals, and then we normalize it by n minus k, where this is the number of observations minus the degrees of freedom. And for simple regression, the degrees of freedom is 2, because I have 2 variables. If I have 3 variables, what's the degree of freedom? 3. Right? So it's just the degree, so number of variables. And it is the number, as the degrees of freedom go up, I divide here by a smaller and smaller number, which makes my standard error large. Right? So for the same amount of residual error, I can have very different predictions. So if I look at the coefficient of determination, yeah.
No, I'm sorry. Right there.
Oh.
So, sorry. I kind of lost track of this. If you divide up those lines, I can see where the sums would equal the whole line. But they're being squared. Doesn't that just kind of throw off that? I mean, 1 squared plus 1 squared doesn't equal 2 squared,
Um,
right? Because those are sums of squares. Or am I missing?
well, actually, the square here is because I'm really measuring. Did I lose the square root here?
Everything that you have up there makes sense. It's just with the squaring, it seems like, doesn't that?
I think the whole right side should be squared and not the individual sums.
Oh, well,
That would get you the sum of the lines linearly. That would break it apart that way, such that you can make a linear representation between, like that graph, right? So that you can break one full line into 2 lines without squaring it. If you're right, if you square, if you just look at the graph, if you square that first data point, that'd be twice as, more than twice as long. Same thing there. But if you squared the whole thing, you would have.
Yeah, so I might be missing some square roots, which you might as well get by squaring both sides appropriately, right? So you're right. I probably messed this slide up a little bit. I was trying to give you the intuition, and one of you correctly found that my simple explanation is wrong. So I think I might have to have either a square root for each of these, right? So then it would be like the square root of 2 is equal to the square root of 1. No, but that's still not true.
I think just square the full sum on the right takes care of the whole problem, because then you're dividing.
No, it still doesn't.
so yeah, the individual pieces are squared allowed, not the whole sum.
Okay, so I apologize. I will fix this and post a solution. I don't know what I was doing wrong, but you're partitioning it into 2 pieces, and maybe this is just to give you a rough idea what it is. It's not the actual math. I probably missed like a cross term or something. I'll figure this out and repost it. But you can really see that there really are 2 things, right? There's how much the line is moving and how much the data is off the line are related, right? It's just the formula is probably not quite right. So, good catch. Okay, so coming back to the standard error. So the standard error then gives us another way of looking at how tight is our line. So the coefficient of determination, which is called r squared, the correlation coefficient, which is called r, but is not related to r squared by squaring. Okay, and I'm just using this slide to point out some of the bad nomenclature that shows up in statistics. So for this line, I have r equals 1, r squared is 1. The standard error is 0. This is a perfect line. The standard error, the slope is 2 and b is 2, right? So this tells me the line intercept formula, right? Very strong correlation. I have r equals 0.97, r squared is 0.94, standard error is 0.3. So this was meant to really give you can see the regression line in each of these, give you some feel for how the data starts looking. So here I have a line that's got 0.51 for its slope, r squared is 0.6, but the error is 1.0. So now it's become a bigger blob. Okay. My suggestion is anytime you're actually doing regression, it is the easiest thing to plot and look at your data. Because I will also tell you that there's times when you go to look at your data and you're doing regression, and the real answer should be, I shouldn't be doing regression. And actually, I have examples of that later, so I'm not going to draw them again now, because now I remembered I added a slide. It's just not here. So the simple statistics, and we go to try and decide what statistical tests we do on it. We'll cover that first, and I'll come back to these other cautionary things. So if I have my line and I do a fit of a plus bx equals epsilon, those where a and b are what I call our sample statistics. And the real world, the population that I'm really worried about, has alpha plus beta x plus epsilon, right? So alpha and b measure the change in y for 1 unit change in x. If b is 0, then there's no effect. So our null hypothesis, if I'm trying to say the 2 variables are uncorrelated, they have no relationship between one another, is that the population has beta equals 0. Beta is the real answer of the relationship between x and y. B is what I get to measure. And now I have to ask questions. Is my regression result statistically significant? So the first question, if I want to say, are the 2 variables correlated? then the null hypothesis is beta equals 0. The null hypothesis is they're not related, and now I have to reject the null hypothesis. That's right, we do all this negation stuff, right? So we want to test if our sample coefficient B is sufficiently different from 0 to reject the null hypothesis and conclude that X is statistically significant effect on Y. So what kinds of tests do you think we use? Okay, well, we're going to do something related to our t-test. We're actually going to use the student t-distribution, but we're going to actually use, so we use the same actual table, but a slightly different test. So we're going to take B, the actual measured correlation, line slope, divided by the standard error in B. Okay, and we're going to use that as t, the student t statistic, which we then can look up. So there is a t statistic or a t-test that you can do. Right? The difference is before our t-test was differences of variables and all this stuff. Right? It was, I already subtracted, it was means, whatever. Now it's B, which is the slope of our fit line, divided by the standard error, which is, in this case, the error of the line divided by the difference between each of the variables. Okay, so this is our variance estimate, and then we have the degree of freedom n minus 2. So we put that in, we get our t-test to get our p-value for is our correlation statistically significant different from 0, and hence can we reject the null hypothesis. Okay. The test can also be conducted on the coefficient of determination, r squared, to test if it's significantly greater than 0 using the F statistic. Different test. It turns out that these two are mathematically identical, right? It's a lot of work to show that all these things break down and become the same, but they do. So I can either use the t statistic or the F statistic. It depends on what test you have, but might as well just use the t statistic because the tables are easier. It's built into Excel. You can always get to where those are. F is a little bit more complicated. It depends on what math tool you have. Now, this is for one dimension. If we do multiple dimensions, right, then we're going to rewrite our regression with two variables. I'm going to have y equals b0 plus b1 or beta 1 x1 plus beta 2 x2 and whatever, right? So for however many dimensions I have, I'm writing it as now a linear combination of multiple variables plus a constant plus an error. Okay. Now in this case, b0 is the intercept. Remember, even though this is a plane, this plane has one intercept, which is wherever it crosses this axis. That's its intercept, and then it has a slope in each of the other dimensions. Right? So it has a slope in x1, a slope in x2, and whatever. Okay. These variables, beta 1 to beta m or b1 to bm, are the partial regression coefficients. Okay? And they give the unit change in y for one change in that one dimension. Okay? And then their product gives us all the planes. So I can slice any one dimension I want off of it. The others are just showing how they're related at the same time. So when I go to do ordinary least squares criterion, I'm going to do the same thing. I'm going to write it down as a variable like this. And I'm going to look at the individual axis predictions. So my error is yi minus the predicted variable. Right? That's my residual. And then I'm going to try and minimize the sum of the squares just like we did before, except now the sum of the squares are measured perpendicular, measured along the y-axis, okay, to the plane. Okay, these are not total or normal least squares in the sense they're still ordinary because they're using each of the inventive variables. And again, it's not that you would implement this stuff you would call a library. Python, MATLAB, everybody's got multiple regression libraries. They're easy to find in any language you want. So the coefficient of determination, r squared, and some of these packages, by the way, when they do correlation, I think I'll probably show you an example in a little bit. They will generally give you r and r squared. They will compute both of them for you so you can sort of see what they are. But again, it's the same formula. It's the difference between yi and the average prediction square, the predicted value minus the average of the true values squared divided by the raw values minus the average of those values squared, similar to the same way it was before. So it's really just the same thing. Okay. Now, this is where you have to be careful from a statistics point of view. The r squared value will always increase each time an independent variable is included. Give me a second, because I might have written that backwards, and maybe it always decreases. And I'll keep going, and I'll check that in a second after I get through this. I always get like plus, minus, left, right, increase, decrease. I don't know which hand this is. Every time I increase a variable, right, I will always do better in my calculation. So if I have 3 points, there's no line that exactly fits 3 points. But there's always a plane that exactly fits 3 points. So I think that probably should be decreased, right? 3 points uniquely define a plane. So the error, if I fit 3 points with a plane, is 0, right? Because it exactly predicts all of them.
R-squared is
predicted error minus the average divided by the real value minus the average. So my prediction error will become 0.
0, right.
So,
Yeah.
but it might become 0 divided by 0.
Yeah, that's what it does.
No, actually, this is minus the mean value of y.
No, the mean value.
So the 3 values won't necessarily have 0 on the
So
bottom.
the top one would be 0. So
Bottom
right
one, yeah.
would be 0.
I think that should be, no. I'll have to go back, but now I'm pretty sure it's increased because we're about to reduce it. So if it
Well,
was,
normally an increased R-squared means that your plane better represents.
oh right, yeah, R squared is larger for better fits, right?
Right.
Sorry, that's right, because of the way it's defined, right? So it increases because it is a better fit. Okay, so we have to be careful then. If I take n points and I do multidimensional regression with n minus 1 dimensions, I always fit it exactly because n points uniquely define an n plus 1 dimensional plane. So I always have a perfect error. So I have to be very careful how many new dimensions do I add. If I only get 4 measurements, I really don't want to try and have 5 variables because I will have 0 error, but I may not have good generalizability. So we talk about this idea for how well does it fit for partial regression of what's called adjusted R squared. Okay, and adjusted R squared is 1 minus R squared times the quantity n minus 1 divided by n minus k, where k is the number of coefficients I put in the regression coefficient. Okay. Now this formula still doesn't quite work if I have more dimensions than I have data, because then the bottom becomes negative and bad things happen. R squared is not allowed to be a negative number. So this is still only true if up to the number of variables I have. So once n minus k is 0, n minus k becomes 1, that's as far as you go. You don't even think about doing regression with 10 data points and 20 variables. Right? You don't have enough data to do, right? Now, the reason I want to point this out is, unfortunately, this is true for linear regression, it's true for nonlinear regression, as long as I'm doing ordinary least squares. Okay? I will tell you that in high dimensions, in lots of machine learning and in various papers, you will see people have 20 variables on 10 measurements. Okay? And the answer is not intuitively meaningful, but it sometimes is. Because if the variables are not actually independent, then I can actually have, even though I have 20 variables, they might actually only represent a 5-dimensional subspace. But I don't know exactly what their relationships are, so there's a bunch of stuff that goes on. So it's not always wrong to have more variables than you have data, but from a statistics point of view, it's a really bad thing to do. Exploring your data and understanding relationships can be helpful, but don't do it and then talk about statistics. Okay, so interpreting your partial regression coefficients. So in 1D we had, right, y equals mx, or y equals bx plus a, right? So one unit change in y changes now in multi-dimensions, just tell us all the variables. So we can ask this question: can we compare these variables of bj, the slopes on the different dimensions, to tell us the relative importance of the independent variables in affecting the independent variable? For example, if I told you that if b1 equals 2 and b2 equals 4 is the effect on x2, is the effect of x2 twice as big as the effect of x1? Right? That's a natural question. Right? Can I use the magnitude of my correlations to say how important is a variable? We just talked about a lot of stuff. This is a question. I want you to think about it for a second.
And they're definitely independent?
They are definitely independent.
I would say yes.
So the answer is no. Okay. So in fact, now that I've told you the answer is no, why not? Can you think of an example of why it can't possibly be that the scale of B matters? Okay, puzzled long enough. So the answer is the size of B depends on the measurement scale for each of the variables. And if you don't even know what those measurement scales are, you can't do anything. But if B1 was measured in feet and B2 was measured in yards, then you're going to get very different answers than if one was measured in nanometers and the other was measured in angstroms, right? All these things, every time I change units, I've changed the relationship between X and Y, right? And I can have huge units. So if I measure something that's actually changing, Y changes in feet, and I measure X in angstroms, right? Then angstrom or nanometers, right? So I'll do meters, or nanometers and centimeters, right? Then if it's really changing at a slope of 1 unit of X equals 1 unit of Y in meters, and then I measure X in centimeters, then 1 unit of X is 1 centimeter. It's a very small unit of Y, so the slope becomes very low. If I flip it around and I measure X in meters and Y is in millimeters, then it's the other way around, right? So units are a huge thing when doing any of these fittings.
I was assuming the same units.
Yep. Well, in lots of computer science stuff, we're actually doing two things that have completely unrelated units. Size of data and milliseconds. Or should it be seconds? Or days? Right? What unit do I use to relate? The things we do in computer science are often relating things that are actually unrelatable. Right? Memory size versus cost. Right? Or memory size versus speed or time. Right? We have all these dimensions that really aren't compatible from a standard units convention. And you don't know how to normalize dimensions, right? The unexpected variations in our data are often very large, right? It becomes even harder as soon as Joseph pointed out, right? If they're also correlated. So if I have two variables, right? Sorry, if I have two dimensions, x1 and x2, and they're correlated, now there's a secondary effect, right, which is their correlation that affects them. So regression coefficients are only directly comparable if all of the units are exactly the same. Now, even if the y dimension is meaningless, if I have dollars and dollars versus age, then I can relate the correlation coefficients. But they all have to be in the same units. And then their actual relative scales matter. And if the units can't be made comparable, then the correlation coefficients can't be compared, ever. You will find papers, however, that do. So, watch out. So comparing the importance of independent variables. So how do we compare if the relative importance of these? We know we can use partial regressions to compare them unless they're all measured on the same scale. However, we can use standardized partial regression coefficients, also called the beta weights, beta coefficients, or for reasons that are really obtuse, path coefficients. All of these are referred to the same standardized partial regression coefficients. And what they really do is they tell us the number of standard deviations of units in Y for one standard deviation of unit in X. Right? So we actually normalize each dimension to actually what we would call z-scores. So if I have data and I have some value X and I divide it by the standard deviation of X, we call that, so that number, right? So that gives us a number that we often call a z-score. And this is a pretty standard normalization, right? And
Should we subtract the mean?
yeah. You're right. Should have subtracted the mean. When I do regression, because of the way regression is doing it, subtract the mean of the regression, right? No relationship is 0. So the mean, so the theoretical model of no difference is 0. But it's always better to do it for normalizing a variable. It is variable minus its mean divided by its standard deviation. Okay, and we call that a z-score. This is a great way of normalizing data because what you're really saying is how far is, here's my distribution, how far is x given a standard deviation, right? This is, you can actually think of this as normalizing it to, if the data was a Gaussian, then this tells me its probability, not a different kind of normalized probability of how likely is it to be this far away. So when this is 0, this is extremely likely, and as I get farther and farther away, the z-scores become less and less likely. So it's like 1 minus the probability of the variable occurring. And now it doesn't really matter what the units are because I'm dividing by, if this has some units of dollars, and this has a unit of dollars, I divided dollar by dollars, and I get something that's unitless. Yeah, not the variance, right? So this is the square root of the variance. Right? So that it becomes unitless. So that's a nice way of normalizing them. And then, modulo some assumptions about Gaussianity. Now the coefficients can be used in standardized form to compare things. However, for computer scientists, remember that making that is assuming certain things are Gaussian. And for a number of computer science processes, this normalization, which assumes the Gaussian data, doesn't really work for data that looks like this, right? So if your data, when you plot it, doesn't look like a giant lump, then this normalization isn't the best thing, in which case comparing of partial regression coefficients is a dicey idea. Okay, so we put them in standard form, which, as I already put that up here, so we're just going to divide them. So then you can do a comparison between them. If I'm going to do statistical tests in multiple regression, you can actually do two different things. You can test each independent variable, because as I said, even though I did this fit, I can test each variable separately. So again, the null hypothesis, that there is no relationship, it's actually the same test we had before, bi minus the standard error. But now our degrees of freedom is n minus k, where k is the number of coefficients in the regression equation. Okay. So the standard error uses the same calculation of t, but I look it up in a different table for t, or use a different formula for t, because my degrees of freedom have gone back up. So this is a little bit like an adjusted r squared, where again we played with the degrees of freedom. And the reason for that is because in multiple dimensions I had multiple extra variables. They allow me to get a better fit to my data. To test the overall model, we take the coefficient of multiple determination, r squared, and we see if it's significantly greater than 0 using the f frequency distribution. In 1D, the t-test and the f statistic were the same. In higher dimensions, they're not. The t-test is only actually applied to every dimension separately. The f statistic goes over all of them. And it's really saying, is there a relationship between the variables? A little bit like ANOVA. It's actually a direct analog of ANOVA. ANOVA said, is there a relationship between these variables? It doesn't tell you which one. It just says there is a relationship. Okay, if I take the overall model and I get something that the f statistic says is significant, I'm saying there's a relationship between these variables. It's not telling you what the relationship is. It's not saying which variables matter. Some of them might, some of them might not. So then similar to the ANOVA, you would then do individual t-tests to figure out which is going on. It is actually possible, but extremely unusual, for the f test to be significant, but all of the t-tests to not be significant. Okay, which is actually different because for playing with ANOVA, you can sometimes get that where ANOVA says there's something significant, But if I try to do a pair t-test for each pair, there isn't significance, because when we do the individual p-test, we do the Bonferroni or whatever that b name was, corrections for the number of tests going on, and sometimes make it so it doesn't show up. It happens less often with regression. But it's not uncommon for regression. As I said, sometimes people do stuff where they fit with more variables, and then they start looking at the b coefficients, and they figure out which variables have no effect. And then they will go back and refit their data with only the variables that seem to have an effect. And that's just a combination of being lazy. Now, in practice, you don't normally do that with more variables than you have data. And you could. You tend to have lots of data, but still too many variables. You go figure out which ones have almost no effect. Okay? But because you're doing this in this axially related model, you can have some problems. I think that's later in my slide, so I'll wait before I get there. I can't remember what I added last week and not what I did. Okay, but when you're going to play with statistics, especially regression, be very careful. Okay, and the reason this graph is meant to give you the idea. These are called Anscombe's quartet. Quartlets. There's 4 of them. All 4 of these have exactly the same mean, standard deviation, correlation, and regression. These 4 sets of data, right? If I were to do any type of statistics test using correlation coefficients and regression, are equivalent. Do you think they're all linear in the same way? No, they're not even close. You look at them and say, yeah, this one's sort of a noisy line. This one's clearly not a line. The errors are very spatially biased. This one is probably a line with some very noisy point on it. But the line should actually be tilted differently. And then this one here has no business being a line, right? But in terms of correlation coefficients, in terms of mean, square, standard deviation, they are all identical. Okay, so this is just a cautionary tale. If you're playing with correlation and regression, look at it, because it's easy to look at. When you get to 1,000 dimensions, it's impossible to look at. 3 and 4, 3, maybe 4, tough. Higher than that, you got to find ways of doing it. But statistics can be particularly misleading. Okay, so how might I actually try, if I'm a computer scientist and I'm trying to do something, how might I explore whether or not the statistics actually represent my data? Here it's in 2D, so it was easy to say, I will draw it and look at it. But if it was in 50D or 5D, you can't. How might I answer some of those questions? Since the statistics are the same, what might I do? And these drawings actually should give you some hints. Okay, so that is a very common and easy technique. No matter how many dimensions I have, I can do lots of 2D plots. If I have 3D, I can slice it this way and this way, and I get 2 2D plots. If I have 4D, this way, this way, this way, right? However many. So there's never a reason to say I can't plot my data. Although when you get to 1,000,000 dimensions, that's a lot of plots. So there's a different problem. But that's good. So that's a good first step, and it's one you should all consider. I have 3Ds, 4Ds, 5Ds. Just do a bunch of plots. Check your data. In fact, I would check your data before you even bother with linear correlation, although it's so easy to call the functions, you can do it either way. What else might I try? There's another technique that's actually very easy to solve these problems.
It may not be easy, but could you collect more data?
I could collect more data, but if I consider these as trends, I can draw these 4 things with as many points as you want and still keep the relationship. That is, I can keep drawing things on this curve, and I'll keep the same line. Right? Right. This one is a little trickier because it's a question of how frequent is that noise. Right. This one here is similar. It's a question of how frequently. But you can imagine there are sampling patterns that will keep it about the same, right? And still have very different things. So there's another, and again, for computer science, this is easy because we often have a lot more control. But even for regular statistician or regular data science applications in other fields, so how might I detect that? So if my relationship is truly approximately linear, what happens if I split those graphs in half? And I take this and I plot regression on this half the data and that half the data. If it's truly aligned, then it should be about the same. And if it's not aligned, so the first, right, these two lines, if I split this third quadrant in half, right, one will be a line tilted like this, the other will become a line tilted very much like that. So if you have a reason, if your hypothesis is truly a linear relationship, then it's easy. Repartition your data a couple of times and see if you get the same results. And if you do, then you're more likely to actually have the real linear relationship. And I can do that in a million dimensions because I just partition my data a couple hundred times in different ways and seeing, am I getting linear relationships? In fact, this is very much related to something we talked about last time for computer science, right? Which is, again, very common for a bunch of computer science problems. In fact, because our problems are often so directly tied to our input data, the only way we actually get statistics is by changing our input data. So we do a process called cross-validation, where I partition my data and I run something. And I partition my data at a different time and I run something. And those two different runs give me different results. That's how I compute my statistics. Right? Well, this is really a variation of that. If my expectations are linear, I partition my data in different ways and I get different answers and I look at those in terms of the statistics. So in fact, I could do multiple linear regressions and now I can ask the question, are they the same? Okay. In fact, if I think of this test, right, the overall model was saying, is there a relationship between these? Right? I can actually do a whole bunch of tests and then ask the question, is there a relationship between them? I can actually use my t-test for each partition of the data and ask, are these essentially equivalent or not? Right? So we get to use the statistics even to help answer, are statistics a good thing? So look at the data, but if you can't afford to look at it because of the dimensionality, you can still use statistics by running multiple subsets of your data through it in an interesting way. The other reason I think it's really good to look at your data is that very often things are not as simple as you might. So if you look at this data, yes, you can draw a correlation line between them. In fact, you get a reasonable correlation. So these are Old Faithful eruptions. The duration here and the time between eruptions on this axis. So Old Faithful, the geyser up in Yellowstone, right? And yes, I could look at that and say there's a line. But do any of you have a better idea what that data represents? Okay, as the bottom part says, right? This is really suggestive. If I looked at this plot, I instantly see two clusters. One at the bottom and one at the top. Okay? Yes, I can do linear correlation, but I would actually say, you know what? There's probably two events going on here, two very different states for this system. Okay? And this is true for lots of things in computer science, where we, in fact, this week's faculty candidate, literally, that's part of what his research has been on the last 5 or 6 years, is that for a bunch of problems, there are what you might consider the normal everyday cases, and then there's exceptions. Right? If I look at run times, normal everyday cases, we have optimized our code for the normal everyday case. Why? Because that's our average. We do lots of things here. But then there's exceptions. Right? Yes, I could put a linear line between them, but maybe I should be doing a better job of modeling them as multiple different states and not trying to say they're really one thing with a variable that matters. Okay? So looking at your data has way more value than just answering, should I do these statistics? Looking at your data gives you an idea, maybe my hypothesis shouldn't be that these are linearly correlated, but that there are actually two different processes here. Okay? And once this was two different processes, I don't have a slide to go with it, but you can imagine saying, okay, I have two different models, and now for each model, I'm going to have a different relationship. This data, you can't quite see it, because I didn't draw it that way, but if you look over here, if I break this data up into this piece, I'm going to actually get a line that fits much more like this, right? So you sort of see the blue dotted line here, right? And then another line over there. I get two different slopes when I break this data up. Again, so before I said that's a suggestion that maybe your statistics have a problem, it's also possibly a suggestion that maybe your data isn't aligned, right? You don't know which, right? Is it 2 lines or multiple pieces? But statistics are not a replacement for you having insights as a researcher. It's your job to explore them. Okay? Statistics are a way of, once you have a good hypothesis, you showing whether or not it's actually valid for that. Okay? And be very careful about spurious relationships. This one might help drive home, which I've talked about this already. Right? Causality is not at all obvious from a relationship. So if we were to do a plot of how many people drown versus the sales of ice cream, this is real data. Okay? There is a strong correlation between sales of ice cream and drownings in whatever's town this was. Okay? And you might have the hypothesis that eating ice cream inhibits swimming ability. You eat too much, you cannot swim. Okay? And how many of you were told when you were a kid you can't go swimming because you just ate? Okay? That result for parents is possibly just a cautionary wives' tale, but some of it is actually based on misinterpretation of data, because eating and swimming are correlated, okay, but not because eating makes you drown. Okay, anyone know what the real relationship is? Yes. Yes, so there's another variable, right? Hot days increase both. When it's hot, I tend to swim more, and when it's hot, I tend to eat ice cream more, right? So there's an underlying variable that drives both of them up, even though the relationship is not causal. So, and it turns out that this fallacy captures lots of researchers. Why? Because they see the relationship. And, as in this case, right, that first part sounds plausible. A plausible theory that relates to variables makes a good story. You tell a story, people read it, they say, oh yes, that makes sense. Okay, when I was growing up, we were told, well, you know, the blood rushes to your stomach, which causes you to get cramps. Okay, unfortunately, while that's true, more blood goes to your stomach, not enough for it to increase your cramps. Okay, and when I was in high school, we did lots of tests because I was on the swim team. We would literally have large things to eat and then go swim a mile or two. It doesn't make any difference. But the story was so compelling. And of course, this helps parents. No, you can't go swimming, you just ate. Really, it's, I don't want you to go swimming, I don't want to deal with that right now. But but you as a researcher, you want to get at the truth. On the other hand, I will tell you that when you're writing a paper, if you can find a story and you can find some statistics to support it, like correlations, you will more easily convince your readers of your story, okay? And so a different way of looking at your statistics is to strengthen your story. Because, to be honest, to many people, this is magic. They don't quite understand exactly how it works. And so if you present it, they think you know what you're doing, okay? At least some. However, if you get even one thing stupidly wrong in your statistics, you can also instantly lose your credibility. Okay? So be careful how you say things. So, in fact, while you might hint at causality, if you say this shows something causality, when I'm a reviewer, that's it. The paper is over because they don't understand what their experiment showed. Why should I trust the rest of what they can do if they can't do basic statistics right? So if I look at income and literacy or literacy and income, regression can't decide. The fact that they did regression on 2 variables they observed and then try and draw a conclusion, to me is a sign of somebody who doesn't know what they're doing. So if you're going to do regression and say it has a meaning, you have to have controlled one of those 2 variables before you can begin to imply. Right? And this is why in science, the standard of good science is what we call a randomized control trial. And it turns out that for computer science, you may not have, how many of you heard that term before, randomized control trial? Okay. It is the standard of science for medicine and everything else. In a randomized control trial, a subject comes in and they are randomly assigned to one of 2 groups, Group A and Group B. Okay? Group A gets a treatment, which we've talked about already. That's what I call like whatever this change is, and Group B doesn't. And then I look at the outcome variable. Okay? That's the closest in the physical world you can get to controlling certain variables. Right? I can't change someone's gender. Okay? But if I bring people in, and independent of their gender, I put some of them in this group and some of them in that group, then I can draw a conclusion where gender is not a variable of interest because I randomized over it. Okay? The worst thing I can have is a variable that I observe but don't randomize. Ideally, I control it, but if I don't control it, I can at least randomize it. Because what I don't want is a bias. And biases creep into experiments, anything involving humans, which can involve human data. Okay, so if I'm looking at, for example, call traffic, and I look at data and I say, well, I'm going to look at call traffic and say, how much of call traffic is personal versus business? Obviously, the time of day at which I collect that data matters. Right? But it's actually the time of day in either the sender's or the receiver's domain, right? Because if I'm calling to New York because it's their business time, then it might so there's a whole bunch of things that may not be obvious, but if it involves real world data and you don't actually control it, then you want to randomize over it. In one of the experiments I did in my previous university, we were actually measuring face recognition, and we were measuring it over periods of months. Okay? Well, one of the things that happens over the periods of months are the angle of the sun changes. So what we were getting in summer and what we were getting in December had very different results. Not because of weather, which is actually what we're trying to study, but sun is weather, right? So I guess it is weather, but right, they're a variable we hadn't control for. And we're having all these weird experimental results. And we were seeing all kinds of interesting trends, but they largely became, as soon as we randomized time, and we did rainy days independent of the time of year and mixed them all together, we got very different results than when we had run them in time blocks, right? So that's the kind of thing you have to be careful of. Anytime you're getting data from someplace, think about how I can randomize every other variable to make it meaningful. So we will take a break now. This is just a joke. The analysis of value of your research is just to make it funny, but things like type 1, type 2 errors, some of the basic statistics, some of the experimental designs, Latin square, full design, all those stuff, that will be the kinds of stuff I will be asking for the final also. We'll go ahead and take a 10-minute break because we actually have plenty of time today, and when we come back, Robert will give his presentation. Any questions on that? Okay.